So, are we ready?
Yes.
Hello, everybody, and welcome. This is Prague seminar for mathematical physics, as you surely know. And nowadays, I'm very happy that I can welcome our today's speaker,
Spyros Afentoulidis.
Yeah, exactly. From our department. He's probably about to say something interesting to us about Dirac operators for algebras and superalgebras. So
Thank you.
the floor is yours.
So thanks very much. So with some of you, we have already discussed the standard setting of Dirac operators, representation theory of Lie algebras. So today I will start directly with the supersetting. I will not say anything about the standard case. And let me start with some notation. So G stands for a complex Lie superalgebra. Of Riemann type. That means that there exists a bilinear form G, which is a non-degenerate, invariant, supersymmetric form. So that means that supersymmetric means the following. When we consider the splitting of G into the even and the odd part, this splitting here is orthogonal with respect to this.
Just a second.
Yes.
Vita has a question. I
Yes.
think you can unmute yourself.
Hi, sorry, it's just that I don't see any video. Did I miss something or is there some problem?
We are displaying and recording. Do the other participants see the video?
Yes.
Okay, so it's problem on my part, so I will try to reconnect. Sorry for the disruption.
No worries. Okay.
Supersymmetric means that this splitting here is orthogonal, and the restriction on G0 is symmetric, while the restriction, the bilinear form on the odd part, is skew symmetric. Okay. So in G1, we have a symplectic form, a skew symmetric non-degenerated symmetric form. So we can fix two complementary Lagrangian subspaces, and for each of them, we fix a basis partial I and xi respectively, with this basis which satisfy the following condition. Lagrangian means that they are isotropic, actually.
Okay.
That means that whenever you take two elements in this subspace, this form is zero. The polarization, if you want, of your space.
The maximum.
Maximal, yes, exactly. Yeah. Complementary Lagrangian subspace. Okay. And we define the Weil algebra of G1 to be the following quotient.
You suppose that the Lagrangian subspaces are the same dimension.
Sorry? Yes,
Yeah.
yes, in this case, yes.
You suppose it.
No, it's finite dimensional and it's
No,
maximal. It can
No, it doesn't matter.
No, G1 is even dimensional, so you can
and
always.
even dimensional.
Yes.
Must be.
And because is it you didn't speak about non-degeneracy of the skew symmetric form?
Actually, it comes from this fact, because whenever you have, if you have a non-degenerate form, and this sum is orthogonal here, that means that on G0 and on G1, the restrictions are non-degenerate. And
There should be also some Jacobi identity.
Sorry, yes, this invariance here means
Okay, this is
invariance with respect to the adjoint fraction.
To jest klasyka super
Yes,
Lie super algebra.
yes,
Lie super algebra.
Yes,
Not,
yes.
sorry.
yes.
All super algebra.
Okay, so we were about to define the Weil algebra, which is the following tensor product. So we will use this notation, W of G1 will be the tensor product, will be, excuse me, the tensor algebra of G1 over the following relations. Let me write them down. So this is the tensor algebra with these relations imposed. Here I put this W here to stress the fact, to insist on the fact that this bracket here is not the bracket coming from the Lie superalgebra structure, but this is just the commutator of the tensor algebra. So in other words, xi and xj commute, partial I, partial j commute, and the only non-trivial relation is this one.
But they are all elements, so are those other commutators then?
Here, it's just I tensor j minus j tensor I. For me, this is a commutator.
Okay, it is a commutator, although the elements are anti-commuting in the original algebra.
Excuse me?
So this is a commutator, although the elements the elements here are like of the G1 subalgebra of the original one.
Yes.
Yes.
This is actually, here you have an associative algebra and you can always define the
Yes.
commutator. Okay, so this is what we call a Weil algebra. And now for this algebra, we have a special module called the Weil the veil module or the metaplectic representation, which is given as follows. So M of G1 is just the polynomial algebra. And the action of the Weil algebra, this action here is given by polynomial differential operators. So in other words, when we take xi here, it acts on this space just by multiplication, and whenever you take the partial I, it acts as the partial derivative on this space. And this is why actually we chose this notation, xi and partial I.
So you say there are no signs, we completely forgot about the degree in G1.
No, just no.
It's just the vector space.
Yes,
the
exactly.
algebra.
Exactly.
If you remember that the x's and del's are odd, this is the Clifford algebra construction.
You mean this one?
Yeah, so well, the Clifford.
Yes, that's true. Yes. Yeah. Actually, it fits with this description. It fits actually in the context of Dirac operators, because for the standard case, instead of this Weil algebra, we use a Clifford algebra, and instead of this veil representation, the metaplectic representation, we use a spin representation. So yes, you're right. Thanks. I never thought it like that, actually.
The parity switches one and Clifford.
Yeah.
Moreover, so here on this space, we have a W module structure, but moreover,
Sorry, can you say again? So I just missed it. So the M is polynomial
yes,
x as commuting variables,
yes,
and then that's just the
Yes.
usual reduction.
okay.
There are boundary branches, the actual one generators that you extend by one.
Yeah.
But sorry, that you was like to say that it acts while defining the representation.
Sorry?
You haven't defined the action, or I consider which action I consider the while for Clifford on the algebra on the symmetric power of these spaces, or on the polynomials.
Here.
Mm.
But the action is given just by polynomial differential operators.
By as they stay themselves.
Yes.
Okay.
Yeah.
So, and here, like dimensions, you're having the dimension of the two subspace system.
Yes, here, yeah. This K can be, yes. It's the dimension of the Lagrangian subspaces. Or if you want half of the dimension of D1. Okay,
So in the non-super case, this would be the spinner.
yes,
Spinner module.
yes.
The super spinner.
Okay, so moreover, MG1 has a G0 module structure, which is given by the following compositional markers. So we choose an element in the G0, the even part of the superalgebra, and then using the adjoint representation, we can embed this element in this spin or in this symplectic algebra. Why? Because the restriction of our bilinear form on G1 is a symplectic form, and the adjoint representation preserves this form. So, in other words, the adjoint of some element here satisfies exactly the definition of for the symplectic algebra. And now there is some map here which embeds the symplectic algebra in the Weil algebra of G1. And this, of course, acts on the Weil representation, on the Weil models. So in other words, and all of these maps are Lie algebra morphisms. So in other words, we have a representation of G0 on this space, on the Weil module. Okay, and now we are ready to define what the Dirac operator is. So let V be a G module. That means a Z2 graded module for G. We define the Dirac operator D of V to be the linear map acting on this space and given by the following formula. So this is what we call the Dirac operator for a Lie super algebra. So the first guy here acts on V by the standard action of V, since we have a V module. And the second argument here, the second factor, acts on this space via this representation. In the standard case, here we have again an action on the module, and here we have just a Clifford multiplication on the spinel module. So this is what we call the Dirac operator. And some properties for this operator. So first of all, it does not depend on the choice of the basis. The second property says that our operator is Z0 equivariant. That means the following. That means that actually on this tensor product, we have two actions. We have the action of the operator, and we have the action of G0. Because G0 acts here and acts here as well. So we have an action of G0 here. And these two actions commute. I mean, the action of G0 and the action of Dirac operator commute. This is what G0 equivalence means here. And so, as a consequence, the kernel of this operator and the image of this operator are G0 modulus. And the third property is the following one. When we take the square of this operator, it has the following nice form. So this omega g here stands for the Casimir element of G. This omega G0 here stands for the Casimir element G0, and here we have just a constant. And actually the Casimir element is somehow the algebraic analog of the Laplacian. And this fact justifies the name Dirac operator, because the Dirac operator is somehow a square root of the Laplacian. So in the algebraic setting, Laplacian is the Casimir element. So in other words, our operator squared gives a sum of Laplacians plus some
I
constant.
don't understand the second term. How is it?
So here we have the Casimir element of G0 acting. Here is somehow the diagonal bending of this action on the tensor product. It's not very important. We have just the Casimir element of G0. Yeah, somehow it's the delta that you have in the Hopf algebra.
So it's not problem.
Yes. Okay. And now we define what we call the Dirac cohomology attached to V as the following quotient. Definition Dirac cohomology. So we define the Dirac cohomology of V to be the following quotient. We take the kernel of our operator, which by property 2 is a G0 module, it's a G0 representation, over this kernel over the following intersection. So we take the kernel again, intersected by the image of V. So everything here is everywhere here we have a G0 modules. So this quotient is a G0 module called the Dirac cohomology. And this module, this quotient encodes very crucial information for V, for the representation V. Namely, we have the following theorem. I will just give a motivation. Actually, this is how everything started.
Oh.
Everything started with the following theorem,
There's
but of course, for the
a question from Victor.
yes.
So I thought this is a good time to ask. You stated that the Dirac operator is independent of the basis.
Yes.
I assume it's also independent of the Lagrangian subspace that you chose first, right? Or does it depend on it?
Yes, in the superalgebra setting, yes. I think it depends on the choice of Lagrangian subspaces.
I don't see why, because if you think of the construction as a Clifford construction, it's basis independent. And
Yes, but then the weights which appear in this veil module will change actually.
But
I mean, when you have a spin module, it is a finite dimensional module.
yeah.
So whenever you act by a Weyl element on the weight, this space is, in other words, the space of the weight is a W invariant. But this is not the case in this context. I mean, the weights appear in the Weyl representation of this form. Think like I don't remember. Rho minus rho 0 plus something like that. I don't remember. And here you can have everything you want. So if you change beta are positive roots, let's say. But if you change your Lagrangian subspaces, this set will change. So I think it is not independent of the choice of Lagrangian spaces.
So I guess that means that there are many inequivalent representations of the type.
Yes, I think so.
Okay.
I mean, I have to think about it, but my intuition says that it depends on the choice of your Lagrangian subspace.
If you look at the even Clifford algebra, depending on the number of generators, the number of spin representations is just one.
Yes.
Maybe two at most. But here you're saying that there are more.
Yes, I think so. I'm not sure. I have to think about it, but I think that.
Actually, I think, Spyro, that there might be a mistake even at the beginning here. So you suppose that you have a non-degenerate bilinear form. You can imagine that you have symmetric bilinear form of signature 1,3. Then you restrict this bilinear form to the vector, to the subspace generated by the vector. Imagine it just 1, 0, 0, 0, 1. And on it is 0, this bilinear form. So it is skew symmetric. Especially it is skew symmetric, and it is not symplectic.
What do you want?
So even the Lagrangians are odd defined in your system.
I'm not sure that
on G0 there is a non-degenerate invariant skew symmetric form.
On G0, on G1 there is a
non-degenerate
yes.
Skew symmetric form.
Yes.
But it doesn't follow if you restrict something non-degenerate, you can get something degenerate.
Yes. But this is not a problem. Actually, this is what we need for. But this is what we need for.
Oh, the restriction is not.
And so I don't have a unicity of Lagrangians even up to dimension. Because if I have zero form, I can choose Lagrangian, any subspace and any complement can be Lagrangian. But
So what's the question actually? I'm not sure that.
what is Lagrangian if you don't have symplectic form?
But we have a symplectic form. Do you want to discuss about it?
No, maybe
later?
I cannot compute it. Okay.
So you say everything somehow depends on the choice of Lagrangian subspace.
Yes, I would say yes.
And also on the complement.
But the complement is a dual actually.
Or you can identify the dual, but the choice of the complement is not unique, right? As well. It is always isomorphic to dual, but it can have many complements. I think.
Yes, I think so. Yes. I mean, you can always take an element from the first phase and
Yeah, and add it
perturb
to
it somehow.
Exactly.
Yes. Yeah. Okay. So why this space is interesting? Because we have the following theorem. It's a theorem actually, but we are used to calling it Vaughan's conjecture. It says the following, roughly speaking, if the Dirac cohomology is non-zero, is non-trivial, then we can obtain the infinitesimal character of V. So infinitesimal character, actually when you have finite dimensional representations, let's say in the standard case, you know that the irreducible, this is irreducible. When we have finite dimensional representations, for example, for the standard case, we know how to classify them. We classify them using the highest weights. But when you have infinite dimensional irreducible representations, you don't have this highest weight theory. So you look for other invariants. One of them is this infinitesimal character, which is actually the way that the center of the universal enveloping algebra acts on your module. This is what we call infinitesimal character. So it is somehow the simplest invariant for infinite dimensional modules. And so this Dirac cohomology says that this theorem says that this Dirac cohomology indicates that it is not zero, it gives this invariant. And this is how everything started. And this is why we started studying these objects. And then, of course, there are many other results which motivate.
But what does it mean that you can obtain infinitesimal character?
That means that
So you don't know it at the beginning.
No, you don't know it. No, actually, the general idea is the following. you want to classify GK modules in the standard case, for example, and then in the super case, okay? And the general idea is, because this is a very difficult question, the general idea is classify representations using the Dirac cohomology, which is an invariant. For example, you want to classify GK modules which have non-zero Dirac cohomology. This is more or less the idea.
So the part of the context was also what obtain means, or?
Yes, of course. Actually, it says that if you can find here a module for G0, a G0 module, which has infinitesimal character lambda, then V has the same infinitesimal character. Yeah. I mean, the conjecture is very precise. The result is very precise. You obtain explicitly the infinitesimal character. But since I didn't define what the infinitesimal character means, because then we need the other results, Harris-Chandra morphisms, stuff like that. I didn't, I just wrote it like that. But yes, we can obtain the infinitesimal character explicitly. Okay. And now, in the second part of my talk, I would like to talk about Dirac cohomology and Lie superalgebra cohomology for the general linear superalgebra with parameters n and n. So now we fix G to be this Lie superalgebra. So this is the Lie superalgebra where the even part consists of these matrices. So here you have m by m matrices, and here you have n by n matrices, while the odd part is while the odd part is just these matrices. And we set G plus be the subspace of G1 of the odd part, which contains these matrices, and G minus to be the part of G1 which contains these matrices. And now for this space, we fix a basis partial I, and for this space, we fix a basis xi. So these two spaces turn out to be maximal Lagrangian subspaces, which are of course complementary. And these bases are chosen to satisfy the previous condition. Here we have one half.
I mean, you multiply and take trade.
Excuse me?
So what does it mean explicitly for G plus and G minus, like this pairing? So you multiply them and take the trace?
Yes, actually, yeah. Yeah, I should have said that this G has a natural non-degenerate invariant supersymmetric form, which is the following one. This is the standard, the super trace of this, probably with some constant, up to some multiplicative constant for some conventions. So yes, everything here is with respect to this supersymmetric form. Okay, now we can again consider the Weil algebra and the Weil representation. But we will see that the Weil representation for this particular case of G has a very nice, has a very convenient form. So we consider again the Weil algebra G1 acting on the Weil module, which is by definition this polynomial space. This is of course the dimension of G plus or G minus. And
Should it be N?
sorry?
Should it be N?
Yes.
14.
Yeah, and
Yeah.
so the trade is.
Do you mean this dimension?
Yeah.
It should be the dimension, yes, n times n. Yes, exactly. Yeah, but for the sake of economy, let's say sure. Yeah, and here we have this action by polynomial differential operators again. But we show that we have another action on this space by G0. But actually, I didn't give you explicitly this action for G0 in the general context because it is somehow complicated. I mean, you have a very long formula with many different indices. But for this case, for GLMN, we have the following proposition, which says that as G modulus, the Weil representation, it is exactly this one. So here you have this mysterious G0 action, and this proposition says that actually this action for GLMN turns out to be the adjoint action of G0 on this space. So here you have the adjoint action. Okay. So not only do we have this isomorphism as vector spaces, but in this case, this isomorphism here is as a G0 modulus when the action on this space is by the adjoint representation. And now, if V is a G module, now if V is a G module, this space, which is the space where the Dirac operator acts, according to this proposition, is exactly this one, as G0 modulus. Here, we just have a one-dimensional character which actually does not contribute a lot to the dimension. So I didn't say anything about these guys. But do you recognize this space here? This is exactly the supersymmetric algebra of G minus. Or if you want, by duality, this is exactly the dual space of the supersymmetric algebra of G plus. And this is exactly the complex which computes the cohomology group for
Sorry, I don't understand. G minus has G minus has grading odd grading. Grading 1, grade 1.
You mean degree 1?
Is
Parity 1?
Yeah. So
Yes.
From the point of view of supersymmetry, it's trivial because there is no even part.
So, but
And you take symmetric power of something. So what is the grading on G minus? What is the sense of saying symmetric on algebra, which is by definition a superalgebra? It is, but with 0 in even grade. Is it just a symmetric? Yeah. Okay.
No, actually, I'm sorry. Actually, you obtain the super exterior algebra of G plus, which turns out to be the symmetric algebra for the for G plus or G minus.
Mhm.
So, excuse me, I said super symmetric, but I wanted to say super exterior algebra, which turns out to be symmetric. Okay.
Yeah.
But the essential here is that this guy here or this guy here, they are exactly the complexes which calculate, which computes the cohomology or homology groups for.
so essentially you shifted the degree by 1, right?
Yeah.
Yes, as you do.
Yes. Yes. And actually, the differentials of these spaces are exactly what they compute. And actually, the differentials are the following. So D, which corresponds to the cohomology, is this one, and the partial is exactly this one. let's call it delta, in order to distinguish from this one. Why? Because actually G plus and G minus are abelian. Whenever you take two matrices of this form and you multiply them, you obtain 0. So here you have just one, just the first sum. You don't have the second sum, which involves lip brackets of G plus or G minus. Okay. And as a remark, we can say that our Dirac operator is exactly 2 times. It's exactly 2 times d minus minus delta. Using this identification. So we see that there is a connection between the Dirac operator and the differentials of homology and cohomology. And actually we will see that they are strongly related. But before that, we will need the definition. So, a G module V is said to be unitarizable public. I should have used if there exists a positive definite Hermitian form let's denote it like that, such that we have the following property. So here Eij stands for the matrix which has as entries everywhere 0 apart from the place Ij, where it is 1. So in other words, you start here with a matrix, you act on U, and this value for the Hermitian form is exactly the value of this guy here. And here you have just the adjoint matrix, the transpose of this one. Okay. In this case, we say that V is unitarizable. And now we have the following theorem. Which relates unique superalgebra and Dirac cohomologies. unilateralizable G model such that there is an extra condition such that when you restrict V G0, so as G0 module, V can be written as a direct sum of a finite dimensional simple G0 modules. So this is the extra condition that we should impose. Then in this case, the Dirac cohomology of V is up to some character. The superalgebra cohomology or the superalgebra cohomology. So I think I don't have enough time, but so this is a second, let's say, a second motivation why we study Dirac operators in the representation theory context, because it is very strongly related to homology and cohomology groups. And then, of course, there are many other results and applications. I will not say anything about the proof. I have a lot of things we can discuss about it, because then there is actually another topic could be, for example, okay, so Dirac cohomology is exactly the Lie algebra or the Lie superalgebra cohomology or homology, but actually there is another result which calculates explicitly this group, for example, which is in the case where V is a finite dimensional representation. I mean, for the standard case, there is a formula which calculates the Dirac, the nilpotent Lie algebra cohomology with coefficients in some irreducible, some simple finite dimensional module. This formula is due to constant. And there's another article published in 2004, which proves the same formula, but for the super algebra setting. So in other words, in the case where V is finite dimensional and simple, we know these groups. So in other words, we know this guy here. Then we can discuss about another talk.
Yeah.
That's all.
Okay, so at this point we thank the speaker for this talk, and if you have any questions, please unmute yourself and.
May I unmute myself?
Yes.
So you, as you said, G plus and G minus are abelian algebras. What is so interesting about the cohomology of abelian algebras with coefficients and some modules?
This is actually a G0 module, and this is why these guys are interesting. Actually, I mean, you construct representations for a G0, or if you want, in the standard case, with the constant formula, you construct representations for K, for example, if you have a DK module. for the maximal compact subalgebra of G.
Well, I mean, I understand that they're just, but just like, in terms of if you momentarily forget about the G0.
But this is actually the essential, because if you just have a Lie algebra, an abelian Lie algebra, just in itself, and you take some module,
Yeah.
for first of all, it will not be a G module, it will be a module for the abelian part.
For G plus.
For G plus, okay? And you construct something. This is not very interesting.
Right. So.
But in this case, we don't have this. Here, the coefficients belongs to some more complicated module, because this is not just a G plus module. This is a G module, and you have an extra action on G plus and on V, which commutes with the differentials, which define these groups. And so at the end, this guy here turns out to have some richer somehow structure. It is not just a cohomology group of something trivial.
Yeah. But I was getting to maybe the observation that if you just treat it as a cohomology of an abelian algebra, well, I don't know, but maybe those are computable. So if, like, can you simplify this further and say like what explicitly are the higher cohomology groups in terms of G plus and V?
In the case that this guy here is finite dimensional, you have this description.
Yeah.
Is by far not obvious and not evident. I mean, even if I give you the result, which I don't remember exactly the form, but it is quite complicated. I mean, it is not trivial to compute.
Even for abelian algebra.
Even for abelian, yes. Yeah, this is, for example, this is the formula. You see? You should spend at least 2 hours just in order to understand the notation.
I don't understand it. So.
Yes. If you want, I can write it on the blackboard, but it doesn't make any sense actually. But I can give you the formula for the standard case, which is much simpler. So for the standard case, I mean, when we don't have G to be a Lie superalgebra, but just a Lie algebra, the constant formula is the following one.
Can you please write down name of the article?
Yes, I will write. What I said actually is a resume of two, probably 3 articles. I will give. I have them here. I can't give you the titles. So in the standard case, where G is a Lie algebra, and V is a GK module. It is somehow a module. It is a vector space which, at the same time, admits an action of G and an action of K.
K is the
maximal compact subgroup of the corresponding group. So the splitting that we have for G, instead of G0 and G1, we have a Cartan decomposition. So this is the maximal compact subalgebra of G, and this is the orthogonal complement. And the formula says that actually, let's suppose that the complex ranks of K and G are equal. The formula says that the nilpotent. Actually, let's say that this is a Hermitian pair. This is in this case Hermitian pair. So the formula says that the nilpotent Lie algebra cohomology with coefficients in V when V is a finite dimensional. So in other words, the highest weight module, let's say the highest weight lambda, is given like that. It is a direct sum so this is a K module, okay? So this K module,
What is U?
U is a, so P can be decomposed into U and U minus.
Yeah.
So it's a upper or lower.
Yeah.
Yes, let's say two maximal isotropic dual subspaces. And so this K module is isomorphic to the direct sum of simple K modules with these highest weights, where W1 is some subspace of the Weyl group. If you want, W1 is exactly the subspace of W, of the Weyl group, consisting of elements which, for which this guy here is the highest weight of some finite dimensional representation. So this guy here should be integral and dominant. Some issues. Yeah. So this is the algebraic analog of Borel-Weyl theorem. Exactly. I mean, from this.
Sorry, this is maybe it's good to say that the decomposition is with respect to what actually?
Yeah.
G, yeah, on the right hand side.
No, everything is K modules.
Of K, yeah.
Of K, yes. This is not a G module, this is a K module.
Yeah,
And these are a simple K modules. Yes, and so good remark from this fact here, you can deduce Borel-Weyl theorem. Exactly. In the geometric setting.
Vita wants to ask something
Yes.
else from the chat, from Tim. You can go.
Thank you. I just wanted to comment that this formula is valid also for the unitarizable modules when B lambda is not just finite dimensional but unitarizable. I mean, then you get different W1, but I mean, in principle, something like this holds. And the crucial part of the proof is that.
Excuse me, in order to understand, you mean this result holds even in infinite dimensional cases, but for unitary modules?
Yes.
Okay, good to know.
Yes. I mean, for the classical Lie algebras.
Okay.
Or I mean, for Lie algebras, not superalgebras.
And
and the crucial part of the proof is that d squared is then actually 0. So I wanted to ask if there are some sufficient conditions for this, that d square equals to 0, or perhaps in this concrete example of GLMN, is it true that d squared is 0 or not?
You mean the Dirac operator?
Yes.
But d square is never 0 actually as operator. I mean, this is not a real differential. It's just by abuse of a notation that we say that this quotient is a cohomology, Dirac cohomology, is not 0. D square is given by this formula with the Casimirs. Did I understand correctly your question?
Yes, but I'm now a bit confused because I thought that there are some cases where the Dirac cohomology is a real cohomology, that you don't have to intersect the kernel with the image.
But this is another question. There are some cases where instead of this quotient, you can just take the kernel of your operator, because kernel intersected with the image is 0. Do you mean these cases?
Yes. Sorry. Yeah, that's what I meant. Yeah.
Square is not 0. What you have is that the kernel of D and the kernel of D square coincide. And so in this case, the kernel of D and the image has a zero intersection. So the quotient is just yes.
Yes, exactly. Sorry, that's exactly what I had in mind. Yeah, you are right. So is it the case here for this GLMN, or do you have some like general sufficient condition for this to happen?
I'm not sure. I don't know.
Okay, thank you.
Yeah, for sure. I mean, there are some probably if you consider some finite dimensional modules or probably unitary modules. Yeah, it could be the case. I mean, for the supersetting.
Okay, another question? If not, let's thank the speaker again.
So let me just say that I'm not a specialist in the supersetting stuff, but the goal of this talk was to trigger a discussion among mathematicians and physicists. I mean, if you can imagine some application